So hello everyone and welcome to today's tutorial. Today we are looking at probability distributions. And we'll start by asking ourselves this question: what is a probability distribution? And briefly, we'll say that probability distribution is a table or a graph or a formula. It can be any of those three, yeah? Which assigns probability values to every possible value of the random variable. Usually the random variable will be denoting it by letter X. In statistics, we were just calling them variables. And you know, we have different kinds of variables. We have quantitative and qualitative. Then under quantitative, we have continuous and discrete. Qualitative, we have nominal, ordinal, and so on and so forth. So we're saying that a probability distribution can be in form of a table or a graph or a formula which assigns probability values to every possible value of the random variable X. Now, what we're calling every possible value of the random variable X, sometimes what we call this part here, this is usually what we call the sample space. And the sample space is the set of all possible outcomes. In statistics, that's how you call it. The set of all possible outcomes is what we are calling the sample space. Okay, so for example, you can have something like this. You can have this variable, let X be the random variable representing number of children in a random household, in, let's say, in Nairobi or wherever, in a certain estate in Nairobi. Then let us suppose that X takes values 0 be the fewest number that can be recorded, or it can be 1, can be 2, let's say all the way up to 6. Suppose those are the possible values that this particular random variable can take. Then you can come up with a table like this, where one of the columns capture all the possible values of the variable in question. That is the sample space. So in our case, this is the sample space. Then if we can know this, if we can know the probability that X is 0, that is the probability that a certain household chosen randomly has 0 children, if we can know that, then if we can also know this, and this, and this, all the way, if we can know this, maybe through historical data, if we're able to know this, X is 6, if we're able to get these probabilities, we know that if we sum them, must give us 1.0. So this is P1, just call it P1, probability 2, P3, P4, and is which? P5, P6, and P7. We know that if you sum those probabilities, you should get 1. So this is an example of a theoretical probability distribution. Number one, the sum of the probabilities will be 1. And then this column here represents all the possible values of the random variable in question. And I'm sure you can see clearly that it is easy to express this table in form of a graph. So you can convert this one into some graph. You can have a graph like this. And because these values of X are discrete, you may decide to center them, and then you have a histogram. So you can center 0 like that. You center 1, 2, all the way 6. Then you can draw now your probability value. So let's say this is P1. Let's say this is P2. Let's say this is P3. Let's say this is P4. These are just guessed values. Let's say this is P5. Let's say this is P6. And let's say this is P7, like that. So you can have a graph like that. That graph also represents a probability distribution. So this is your random variable X. Then on the vertical axis, you have probabilities. Then in most of the cases, you know, when you have a table like this or a graph like this, you may not exactly know what is the name of that probability distribution. So to help us be able to identify the exact probability distribution, we use formula. So this one, if there's a formula that we can use to generate these probability values for each value of X. If there's a formula that can generate all those probability values for every, for a given value of X, then that formula will also be representing a probability distribution. So in a nutshell, that's what we call a probability distribution. This definition, or the nature of a probability distribution, has very close resemblance with what we call a frequency distribution in statistics. So because actually a frequency distribution is a table like this one, but now instead of having probabilities in this column, you have frequencies. So you can have X is 0, then you have the frequencies here. And then the sum of all the frequencies will total to the size of the sample or the number of subjects that were studied. Okay, so basically that's what we call a probability distribution. Then we say that probability distributions can be broadly classified into two. We have what we call discrete and continuous. These two names, if you remember well in the introductory to business statistics, these two are they are the two classifications, or they are the two types of what we call quantitative variables. You remember what are quantitative variables, you realize that they can be classified into discrete and continuous. So basically, when we talk about probability distributions, we will also be dealing with quantitative variables. We'll also be dealing with quantitative variables, things like age, things like what? Things like number of children or number of subjects, and so on and so forth. So discrete or continuous data. So examples of probability distributions. We have many probability distributions, but in this class, our focus will be on what we call binomial Poisson distribution. Poisson is capital P here, because it's the name of a person. Then we have what we call the normal probability distributions. There are many others, but in this course, we are only interested in these three. So these two are discrete. These are discrete probability distributions. And then this one, this is one of the most important probability distributions. This one is continuous. probability distributions or distribution. One major distinction between discrete and continuous is that discrete probability distributions, they are based on discrete variables. They are based on discrete variables. And the random variable X takes an exact takes exact values. So the word exact here means we shall be using equalities. Here we use equalities. If you are not given equalities, you reduce the problem into, or you simplify the problem into equalities. Now, continuous variables, they are based on, continuous probability distributions, they are based on continuous variables. And here, probability, let's say here we calculate the probability that, so here we calculate probability that, here we calculate probability that X lies within a given interval, as opposed to X taking an exact value. So in the case of continuous probability distributions, we do not look at, so here, let's start from up there. Here we look at something like this, X is equal to something. For example, X is equal to 5, or X is equal to 12.8. But here, we talk about X being in the interval, or you can say X being less than, or you can talk about X being greater than X1 or less than X2. So we calculate those probabilities, probability that X lies within such an interval. So if in case of a discrete probability distribution, you are given something like this, you have to reduce this problem into a problem of a summation of equalities. For example, if you are told X is less than 2, then you have to break it down into X is equal to 0 plus X is equal to 1. That is X is less than 2. If you are given that in the context of discrete. So in the case of discrete, we use equalities to calculate probabilities. But here we maintain the inequalities. We never ever use equalities. You can talk about less or equal to, but you cannot talk about being equal to. So that's a major distinction between discrete and continuous probability distributions. So let's look at the binomial distribution. So binomial distribution. So the binomial distribution is fully defined by two things. So this probability distribution is fully defined when you have n, that is the number of trials, and p, probability of success. In other words, for you to solve a problem in binomial distribution, you must have those two guys, n and p. And here are the characteristics of the binomial distribution. This is what we'll check to know that we are dealing with this particular distribution and not any other distribution. Number one is that the number of trials, n, is fixed and finite. The number of trials, n, is fixed and finite. Fixed means that we know it in advance. We know it in advance. And then the number is countable and known. Fixed and finite. For example, we can talk about, we toss a coin 1,000 times. So in this case, we know in advance that we're going to toss the coin 1,000 times. So that is fixed, and we will not toss it 999. We will not toss it 10,000 times. And then this 1,000 is a finite number, is a known number, is not infinite. The opposite of finite is infinite. So here we deal with finite values of the trials. And we know the number of trials in advance before we start the experiment. The second one is that the probability of success, let me skip that and say this, very important. Each trial results in one of two possible outcomes. In other words, we are saying every trial has two possible outcomes, and one of them must occur. Every trial has two possible outcomes, and one of them must occur. For example, when we toss a coin, there are two possible outcomes: heads or tails. If you toss a coin, there are two possible outcomes, and one of them must occur. So one of the outcomes is labeled as success. So you call one of the outcomes success, especially the ones that we're interested in. The outcome of interest. So this word success here does not have a literal meaning. It is just a label. It's just a label. Then the other one, you call it failure. This is the outcome that you are not interested. The outcome that you are not interested. So maybe you are tossing a coin and then you want to count the number of times the head occurs. So once you're done with that experiment, you will again, or maybe somebody else will be tossing again 1,000 times, and they're also recording how many heads they're observing. Maybe a third person will be conducting the same experiment, then recording the number of heads that are occurring. So in this case, the head is your success outcome, and the other outcome is known as failure. So this means that the two outcomes, this statement just means that the two outcomes are mutually exclusive. That's what we call it. We say they are mutually exclusive, meaning that they both cannot occur in the same trial, and they're also collectively exhaustive. To exhaust is like to deplete or to make complete, or to finish. So the two outcomes, they represent all the possible outcomes in that particular trial. So the two outcomes are exhaustive. They're exhaustive. Nothing remains. There's no other outcome that is outside those two. That's what it means. So that's number two. So very importantly is there are two possible outcomes. So if you have an experiment which has more than two possible outcomes in every trial, that cannot be binomial. Unless you want to collapse some of the outcomes, you compare them with one of the outcomes, then, or you want to group the outcomes into two, then that particular outcome, that particular experiment will not be binomial. Number three is that the probability of success, the probability of the success outcome remains constant throughout the experiment. the probability of success, we have already explained what is a success outcome. So we're saying the probability of the success outcome remains the same throughout the experiment. For example, if you're tossing a fair coin, 1,000 times, the probability of head, remains 0.5 or half throughout the experiment. Doesn't change. From trial 1 up to trial 1,000, the probability of observing a head remains the same. If you are dealing with what we are calling a fair coin. A fair coin is a coin which is equally likely, where the two sides are equally likely. Then finally, number 4 is that the fourth characteristic is that the outcomes, let's say the outcome of every trial is independent of the outcome of every other trial. In other words, all the trials are independent. Independence is a concept that you might have come across in Introduction to Statistics, where we say that if two events, A and B, are independent, if A and B are independent events, so you relate, say, probability of A, given that B has occurred, is the same as probability of A. The left-hand side, there's a condition. If we know that B has already occurred, then what's the probability of A? That's the left-hand side. But the right-hand side says it is equal to the probability of A, whether B has occurred or B has not occurred. So you can say, probability of A, given that B has not occurred, still the same as probability of A. So this means independence. Because you can see the occurrence or non-occurrence of B does not affect the probability of A occurring. You can also reverse and say probability of B, given that A has occurred, is the same as probability of B. Or you can say probability of B, given that A has not occurred, is the same as probability of B. So this again also means independence. So if independence is assured or is confirmed, then, so this one should have come here. So if A and B are independent, the probability of both occurring, that is, probability of A and B occurring. Sometimes we write this one as probability of AB, or sometimes you write a probability of A intersection B. So this is the same as probability of A divided by probability of B. So if two events A and B are independent, then the probability of both occurring is given by the product of the two probabilities. For example, if you are tossing a coin and then you believe that if you toss a coin, you know that there are two possible outcomes, H and T, and you believe these two are independent. If you believe these two are independent, then let's say you are tossing a coin twice. Let's say a coin twice, you're tossing a coin twice. So twice here means that the number of trials is 2. So the probability of getting head and tail, the probability of getting H and T in the two tosses is just the same as probability of getting head and probability of getting tail. So if this was a fair coin, for example, if this was a fair coin, then probability of getting the probability of getting H and T, or both head and tail, will be a probability of head and probability of tail. Is half, is a quarter. The same case, if you are looking at probability of getting head in the first toss and head in the second one, it just be probability of getting H, which is half times half. The same case with TT, which again will be half times half, a quarter. I think you must have seen in your other subjects that you are always saying that this is a quarter, because we are assuming that the trials are independent. So if they're independent, we just multiply the individual probabilities to get the probability of both occurring. So that's independence. So those are the 4 characteristics of the binomial distribution. So all those must be satisfied for you to assume a given random variable has the binomial distribution. Now, how does the formula look like now? The formula of the binomial distribution. And we say, let X be a random variable. Be a random variable using let's say, let X be, well, let me say that, following a binomial distribution, I should have said, let X be a binomial random variable. Now I don't want to keep removing it. So let X be a random variable following a binomial distribution with number of trials equal to N, and probability of success equal to, as we mentioned when we were starting, we said that the binomial distribution is defined those 2 items, N and P. So once you have those 2, you are sorted. Then we also mentioned that for discrete probability distributions, we talk about the probability of getting an exact value of X. We talk about the probability of getting an exact value of X. So if you are not given a question involving an exact value of X, you have to reduce it into a series of exact values of X. So we say the probability of obtaining exactly, that word is very important, exactly X successes and trials is given by this formula. So we say probability that X takes exactly X values, X takes the exactly X, the value X is given by N combination X, P or X, then Q or N minus X. Most of the time you will find me writing it like this, P, that X is X. That P stands for probability, is equal to N. And I have this small letter P, then Q minus X. So here, X is the variable. X is the random variable. Something like what? Number of heads. Heads in a coin experiment, for example. If you check the class notes, we'll see more explanations as to how we can come up with these. Then X, these are the values. These are the possible values. And these possible values, they take number 0, 1, all the way to n. So these are numbers, 0, 1, all the way to n, where n is the number of trials. N is the number of trials. This is also the number of successes. The number of successes. Then P is the probability of success. Then what I'm calling Q is 1 minus P, is the probability of failure. You will notice that P plus Q will always be equal to 1. This is the issue of collective exhaustive. The probability of success plus probability of failure gives us 1. Now, there's this item here I want you to pay attention to. What we are calling N. This one is read as N combination X. N combination X. Or you can translate it to the number of ways of choosing X successes in N trials. The number of ways. So it's a counting technique. So this is a function which helps us to count. It's known as a combination function. Another function which is related to this is called permutation. And there's also another function which is related to both, which is known as factorial, okay? So we'll be using the factorial and the combinations because the combination is defined using factorials. So the combination tells us, this guy here tells us the number of ways of choosing X successes from N trials. And the condition is that X must always be less or equal to N. In other words, you cannot choose the number of successes from a lesser number of trials. For example, you can't choose 10 successes from five trials. Doesn't make sense. So you will be seeing something like this. And the good thing is that you'll be evaluating that part using your calculators. For example, in 10 trials, you choose, let me use a smaller number. In 3 trials, you choose 2 successes. So if you check your calculators, you'll see this function. You'll see this function on your calculators. So that is a function that will help us to compute that part. In my other class recording, I've illustrated how the counting is done using a small example. I gave an example of n is equal to 3, and then we were able to see how many times we can combine them into 2s, or combine them into 3s, combine them into 1, and so on and so forth. So, but for now, we'll go straight to the application of the function from the calculator. So I don't know whether some of you are able to see it. I don't know whether some of you are able to see that function. So we have seen 3 combination 2 is 3 from our calculators. 3 combination 0 is 1. 3 combination 1 is 3. And 3 combination 2 is 3. We have also done 10 combination 5, which is 252. And we have illustrated basically what it means by combination. For example, if you have 3 subjects, A, B, and C, and you want to choose one of them, then there are 3 ways of choosing one of them. You can either choose A alone, or B alone, or C alone. Those are 3 ways if you count. Then if you have 3 subjects, you want to choose 2. So you can choose A and B, you can choose A and C, you can choose B and C. Those are 3 ways again. So that is, those are the answers we were getting earlier on. The same case with 3 combination 3 and also 3 combination 0. Then we were saying that if you look at this formula here, these powers, the powers of P and Q, if you add them, if you take this power plus this power, you'll always get N. You'll always get this guy all the time. The power of P plus the power of Q must always be equal to N for any given, for all values of X. So let's have an example now to illustrate how binomial distribution can be applied to solve some problems. So let's consider this example where we're saying that the probability that a randomly chosen matchstick breaks on being struck is 0.45. In a matchbox containing 50 matchsticks, what is the probability that when all the matchsticks are struck from an 1, none breaks? 2, exactly 2 break. At least 2 break. At most 1 break. Between 5 and 8 break. And we're assuming that the number of matchsticks that break on being struck follow the binomial distribution. So once you are told that the random variable in question follows the binomial distribution, you need to ask yourself, what is N? And what is the number of trials, which we said must be fixed and finite. So a matchbox has 50 and we are striking all of them. So that is our N. N is 50. And the probability of success is 0.45. A good starting point would be you define your variable of X, your variable of interest. Let X be the number of matchsticks that break on being struck. So that is your random variable, X. So here we are saying that X has binomial distribution. X has binomial distribution with number of trials N and probability of success P. I should be saying here N is equal to 50. And P is 0.45. So once you get those two, you are good to go. From 1, probability that none breaks. None means 0. So probability that none breaks is the same as probability that X, which is the number of matchsticks that break on being struck, is equal to 0. We saw from the formula, I'm going to apply this formula here. So now what we have done is that we have put a 0 here. And we'll put a 50 there. We'll put a 0 there. we'll put a 0 there. We'll put a 50 there. We'll put a 0 there. Then where there is P, we put 0.45. And then where there is Q, we put 1 minus 0.45. Which is 0.55. Then we simplify. So let's do that. So here we need to say this is the same as 50 combination 0 times 0.45 raised to power x, which is 0, times, in this case, Q is 1 minus 0.45, which is 0.55. So 0.55 raised to power 50 minus 0. If you add the two powers, you must get n. If you're not getting that, you know there's a problem. So someone simplify that for us. And you write the answer in the chat. So if you evaluate that using your calculator, the answer appearing on the screen of your calculator would be 1.042640222 times 10 raised to power minus 13. It looks like this, 1.04264 etc times 10 raised to power 13. This tells you that you need to move this decimal place here 13 times to the left. It's negative. So negative means you move it to the left. So we are moving it from, we are moving a decimal from here all the way 13 places backwards. So from here, so these are very small probability. So if you count them, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Then you move your decimal to this place. So that is how small the probability is. So most of the time when you're solving such problems or problems like this, you'll be asked to write your answer, let's say 4 decimal places. So if you write this answer to 4 decimal places, the answer will just be 0, 0, 0. This is 4 decimal places. So in some of the questions that I've posted on the assignment, you'll be required to write your answer in 4 decimal places like that. So if you write that, then you should be graded as a correct answer. So, but you need to recall that probabilities are numbers between 0 and 1. So you cannot get a probability value which is outside that interval. A probability value can never be negative. They are non-negative and they're always less than or equal to 1. They can be 0, they can be 1, but not outside that interval. So be careful when you're reporting probabilities so that you don't report the wrong values. And also notice how your calculator is reporting numbers. Most of the calculators will report your values in standard form. So like this, whatever is showing on your calculator is standard form, which is a 1 point something, then times 10 raised to something else. Okay, so this power here tells you how many places the decimal will move. If this power is positive, you move the decimal on the positive direction, that is on the right-hand side. If the power of this guy here is negative, you move the decimal to the left, and then you put zeros. You put zeros to the left of the first digit there. So that's Roman 1. Let's look at Roman 2 as I answer some question from someone. Roman 2, exactly 2 will break. So probability that 2 break. Same as probability that x is exactly 2. Same as from 50 use 2 times 0.45 power 2 times 0.55 power 50 minus 2 is 48. So let's evaluate that. Then you send the answers in the chart. So just like Roman 1, we are observing that this is the answer to Roman 2. And all the time we prefer to express probabilities in decimal form, not in standard form. Avoid using the standard form in this case. So usually 4 decimal places are sufficient, but it's always good you follow instructions. Just check what the question is requiring you to do. So next one, we are looking at probability that at least 2 will break. That means 2 or more. So when you say 2 or more, it means that we're talking about probability that X is 2, or X is 3, or X is 4, or the story continues, or X is 50. That's what we're talking about. So we need to calculate probability that X is equal to 2, like the one we computed in Roman 2. You also compute a similar one for X is equal to 3, and so on and so forth, which will take you a very long time for you to do that. So to help us move quickly, we use the complement rule of probability, where we say this is the same as 1 minus probability that X is less than 2. So this is greater or equal to 2. So we reverse it, but we take away that from 1, less or equal to 2. And less or equal to 2 means that the same as 1 minus probability that X is 0 or X is 1. When you say X is less than 2, you mean X is either 0 or X is 1. So we need to compute those two. We sum them up. So this is the same as 1 minus probability that X is 0 plus probability that X is 1. Please notice where I've put my brackets. Let me highlight them so you can see them. So you compute these two probabilities, X is 0 and X is 1. You sum them, then you take away that sum from 1. Already we have X is 0. So we need to compute X is 1. Then we sum them up and take away that sum from 1. So your calculator is able to perform that function without keeping these decimal numbers. You can press this entire value from your calculator. Then you plus 50 combination 1 times 0.45 power 1 times 0.55 power 49. You get that sum. Then you say 1 minus the answer. So you get the answer without having to record or to do it stepwise, which will give you the most correct answer. So we have already looked at Roman 3, where we saw that the probability is very close to 1, approximately equal to 1 there. Then I want you to try this, probability that at most 1 break. At most 1 means either 1 or less. And 1 or less means 1 or 0. So you need to compute those two. We already have this probability and also this probability from here. So you just need to plug them in, then you sum them up. So we need probability that X is 1 or X is 0, probability that X is 1, then you sum them up. Then the other one between 5 and 8 in a similar way. So here we're talking about Roman 5, where that X is between 5 and 8. So you need to compute probabilities for all the discrete values between 5 and 8. So this is same as probability that X is 5 plus probability that X is 6 plus probability that X is 7 plus probability that X is 8. The same way we were doing the earlier ones. You compute them, then you sum them. And basically that's how you compute probabilities using the binomial formula. So in conclusion, before you conclude, let's say this. And standard deviation of a binomial random variable. And the mean which we usually denote by mu, is given by the number of trials times P. And variance, I will talk about variance first. Variance is given by NPQ, N times P times Q. You know that standard deviation is the square root of variance. The square root of Q. For example, if X has binomial distribution with N is equal to 100 and P is 0.3. If that is what you have, then mu, the mean of X, is N times P, is 100 times 0.3, which gives us what? 30. Then if you want to get sigma, variance is usually denoted by sigma. Sigma squared, and this is denoted by sigma. And you can say sigma is square root of N times P times Q. Q is always 1 minus P. Okay. Which will give us 4.5826 when you round off 4 decimal places. Okay, so that's basically how you find the mean and standard deviation of a binomial random variable. And that is the end about binomial. I want us to quickly look at the other type of discrete distribution, which we call the Poisson. Which mentioned is also a discrete distribution. And here are the characteristics of the Poisson distribution. And I want you to compare and contrast these characteristics with those ones of the binomial distribution. So the situation might be similar to the one of binomial distribution, but here N is infinite. Either uncountable or unknown, or sometimes or extremely large or very large. Usually we say N approaches infinity. Say that the number of trials in this case will be approaching infinity. The number 2, P is very small. That is, probability of success is very small, which means that P approaches 0. That's why we say that the Poisson distribution is used for rare events. Events which do not occur quite often. For example, in our country, we can talk about earthquakes. Earthquakes are very rare in our country. And also you can talk about accidents, number of accidents. Let's say here we're talking about the number of earthquakes in a year. The number of accidents in a day, let's say in a busy highway, you see rare events. So if an event is rare, the probability of occurrence is very close to 0. Basically, that's what it means. The most important property, which summarizes what we have talked about up there, is that the mean is approximately equal to variance. The mean is approximately equal to variance. That is, mu is approximately equal to sigma square. And we can illustrate that using a binomial distribution. For example, the Poisson distribution can be used to approximate the binomial distribution when 3 is satisfied. And what does that? That is, we're talking about when mu is equal to sigma squared. So we're talking about when NP, that is our mu, is equal to NPQ, which is our variance. And when can that be equal? When can this be true? When this is approximately equal. That's what I mean. If you check this, this is explained by Roman 1 and 2 above. Because if you divide both sides by NP, you will have 1 approximately equal to Q. If you divide both sides by NP, if you divide here by NP, and also here by NP, you'll be left with 1. You'll be left with Q is approximately equal to 1. And when is Q approximately equal to 1? That is only true when P is approximately equal to 0. Because we know if you take P plus Q, you always get 1. So if we are saying that Q is very close to 1, or is approximately equal to 1, then it means that P is very close to 0, which is what we said earlier. And we know that P is very close to 0 for rare events, and especially when that is combined with the trials being too many, or sometimes when the number of trials is also unknown or uncountable or extremely large. So sometimes you can be given a binomial distribution, then you want to use a Poisson distribution to approximate it. Then you only do that in cases when this is true. If this is not true, then your estimates will not be reliable. Okay. Now, the Poisson distribution, so we say that, so now let's talk about the formula. We say that the Poisson distribution is fully defined by one parameter. By the mean parameter, which we call mu. So this is the mean parameter. For example, you can be talking about the mean number of accidents per year. Now let's say per year on a certain highway. On a certain highway, yeah. Or maybe mean number of accidents per year in a certain workshop. So usually is the number and also this unit of, let's say, time. So we report this mean as a rate of occurrence, the mean number of successes per unit time or per unit or any other measure of occurrence or frequency. So there's an interval somewhere. There's always some interval somewhere. Okay, so the formula looks like this. So the probability of observing X successes. This is small letter x. X successes. Let's say the probability of observing 20 accidents in a year in a given interval is given by this formula. So we have P for probability that X is equal to small letter x is equal to e raised to power minus mu, e raised to power minus mu, multiply this by mu power x, divided by something we call factorial, x factorial. This thing looks like an exclamation mark. It's known as factorial. Of course, here x is a random variable. For example, the number of successes. Then x takes the values 0, 1, all the way to infinity. It takes these values all the way to infinity. Remember, n is unknown, or n is infinite. Then we have E is a mathematical constant, which you'll be obtaining from your calculator. And you need to learn how to get that value correctly. This number is always around 2.78 something. Huh? You don't need to memorize it, but you need to know how to get it correctly. So let me write the approximate value for your reference, 8281. So that number is available on your calculators. You will confirm if you're able to obtain it. You can either use the shift function. If you use shift function, you must say power 1. You must put the power. Or you can use the alpha function. Once you use the alpha function, you just press and get the answer instantly. So choose whichever. We prefer using the shift function because most of the time we'll be having e power something. But if you want e power 1, the same as e, then you must specify this power on your calculator. So just press the function written like this. Then you open brackets and put power 1 like that. So on your screen, you'll see something like that. That is e raised to power 1. That's what will give you this number. If you're not getting this number, just know that you're doing it the wrong way. Then here we have, of course, mu. This is a parameter, the mean number of successes in a given interval. Most of the time it will be an interval of time. So it will be per day or per hour, per minute, and so on and so forth. Okay. Then we have this guy here. This is read as x factorial. This is how you read it, x factorial. Okay. X factorial. And x factorial is a mathematical function which evaluates this number. Let me give an example to make myself clear. For example, 3 factorial . 3 factorial is the same as 3 times 2 times 1, which is 6. If you have 7 factorial, the same as 7 times 6 times 5 times 4 times 3 times 2 times 1. So you stop at times 1. But instead of doing this, you just evaluate. There's a function on your calculator which is written x factorial. There's a function like that which does this computation. So if you, I think you need to shift. So you press 3, then shift, then you press that factorial function, then you press equal. So this will tell you that the answer is 6. If you do the same for 7 factorial, the answer is 5040. So I want you to try, check your understanding. Try 4 factorial. At least you know the answer to 4 factorial. You can also try what is 10 factorial. You can write the answers in the chat, then I'll be checking them. So let's move on. We have seen that 10 factorial is 3628800 and so on and so forth. So let's have an example to illustrate how we can compute probabilities using the Poisson formula. And here you are given a question which says that patients arrive at the emergency department of a certain hospital at random at the rate of 10 per hour. At the rate of 10 per hour. Find the probability that exactly 2 patients arrive in a given hour. And number 2, find the probability that in a 120-minute duration, exactly 10 customers arrive. So let's solve those 2 questions and then we shall be done with that part. So solution, we need to know mu, the mean number of successes by given interval. In this case, mu is 10. Okay. And that's the only thing we need to know under Poisson distribution. But we need to know that this is per hour. So that mu is 10 is only true per hour. So if you change the interval, then we need to revise that mu. So Roman 1 says probability that we have exactly 2. So this is the same as e raised to power minus mu times 10 raised to power x, which is 2, divided by 2 factorial. So you press the exponent, then you raise to power minus 10, multiply that by 10 raised to power 2, divide everything by 2 factorial. You can press everything once. You get the answer 0, 0, 0, 2, 2, 6, 9, 9, etc. Yeah? Approximately in 4 decimal places, 0, 0, 2, 3. So that's the probability that there will be exactly 2 patients arriving in a given hour. Now, the other question is slightly different, and I want you to be cautious. You are given a different time interval. The interval here is 120-minute duration, whereas this one was 1 hour, which is 60-minute duration. So we need to recalculate the value of mu by just doing simple cross multiplication. So if mu is 10, this is for 60 minutes, that's 1 hour. You need to compute a mu, which you can call mu star if you have 120 minutes. So using simple cross multiplication, this will be mu star is equal to 120 times 10 divided by 60, which will give us 20 times 1, which is the same as 20. So that's the new mu that we shall be using to answer Roman 2. And the other part will remain. So probability that we have x being equal to 10, this is the same as e raised to power mu, which is 20, times 20 raised to power 10 divided by 10 factorial. So please notice that what is important is that you need to convert, you need to transform mu to fit the interval that you are given. So that means here we'll take exponent minus 20 times 20 raised to power 10 divided by 10 factorial, which is 0.00, let's say 581. 0.0581. So that's how you can deal with Poisson distribution if you want to calculate probabilities. Please notice that here we said that under the Poisson distribution, the mean is equal to variance, and this is equal to that. So this value here, this 10 here, which is our mu, is also the variance. So in case you asked what's the variance, or you have a problem which involves variance and mean in a case of a Poisson, then just know that mu is equal to variance. That's all. Then finally, I want us to move to the normal distribution. Which we said is an example of a continuous probability distribution.